In this lecture, I want to introduce the basic concept of how multi-layer neural networks can be trained, the backpropagation algorithm. So first of all, we define a cost or loss function C, which is the quantity that we want to minimize. So we turn our problem of finding optimal parameters into an optimization problem in which we minimize the function C. We assume here that this is a supervised learning problem, so C depends on the inputs x and the labels y, and also the parameters that we're searching over theta. And we are searching the argmin of over theta of C. So we're searching the set of parameters which minimize C, and we call this result, those best parameters, theta hat. If we have a maximization problem instead of a minimization problem, we just turn it into a minimization problem by maximizing minus C. So in that case, C is a score instead of a loss function. When we write C, then we will often just write C of theta, and we will omit x and y, just for brevity. Okay, so let us look at an example. So suppose we have input features x and we have labels y and neural network prediction y hat. And then for every sample I, we compute the error vector, which is the difference between the predictions and the labels. So now let's consider two different types of cost functions or loss functions. So first of all, consider we want to do a regression. So we want to approximate a function whose function values are given at the output for the training positions xi as labels. And we want to approximate these labels as good as possible using our neural network predictions. In this case, for example, what we can do in least squares regression, we minimize the square norm of the error vector summed up over all data points. So that's the L2 norm or the mean square error of these error vectors. Other example, classification. So suppose we have k categories. For example, in the MNIST image recognition problem where we're trying to read handwritten images and sort them into categories 0 to 9. We have k equals 10 categories, and the inputs are the pixels or the pixel activations of the image. All right, so often what we do is we represent the output as a one-hot encoding. So we have a vector of, in this example, 10 values, and in the label, so the reference value, there is one of these 10 guys equal to 1, marking the class that we expect to find, and every other output is 0. And in a classifier, the prediction, so the output of the neural network, will typically also have an output vector that has 10 elements, obviously, and non-negative outputs, and whose sum will sum up to 1. So in the ideal case, it would predict one output equal to 1 and the other 0, and this output it predicts to be 1 will coincide with the one that is equal to 1 in the label. So now in classification problems like this, we typically use probabilistic loss functions such as the categorical cross entropy, but we haven't talked about that yet, and we will talk about this a bit later in the lecture. So for now, just consider that we are comparing these outputs and the corresponding labels in the same way as we do for regression. So we compute the error vector between these two vectors, and we compute the mean square error over them. And so that's it. So that is not the ideal way of doing classification, but conceptually that is fine for now. So with this, we have defined a cost or loss function, and it is clear what we want to optimize. Now, how do we optimize? How do we find parameters theta that minimize the cost function or loss function C? So usually neural networks are trained with some sort of gradient descent. The basic gradient descent approach is as follows. We initialize the parameters at some initial value theta 0, and then we go through t time steps or until some convergence criterion is met. And in each time step or each iteration, we compute the gradient of the loss function with respect to the parameters of the neural network. And then we update the parameters and we change them a little bit downhill the gradient. Yeah, so the gradient is a vector in our parameter space which points in the direction in parameter space that if we go along this direction, the function c increases, but we want to decrease this function, so that therefore we go in the opposite direction against this gradient downhill. So this is gradient descent. In practice, we almost never use actual gradient descent in neural networks. Usually we use stochastic gradient descent or some form of that, but we will talk about that in the next lecture. So now the question is, how do we compute the gradient? And this is not particularly trivial because neural networks are complicated functions. So in particular, networks are functions of functions. Often we have these multi-layer structures, so we have functions of functions of functions. So clearly, we will need the chain rule of differentiation. But we do not want to work out the functional form of the derivatives every time on the paper that we build a neural network. We want this to be completely automated. We essentially just want to define what is the architecture of a neural network. We are willing to define the derivatives of the individual components, the individual functions that are used in the neural network, such as activation functions. And then we just want to plug things together and have a program that figures out everything automatically, or figures out automatically how to compute the gradient and how to update the parameters as a function, as a part of the training algorithm. And that is what is leading to the backpropagation algorithm. So the backpropagation algorithm is essentially just an automated way of using the chain rule of differentiation to automatically construct gradients for multi-layer neural networks. Let us derive the backpropagation algorithm for a multi-layer perceptron. So as a reminder, some notation about multi-layer perceptrons. So we have capital L layers. We index them by little l going from 1 to capital L. So layer 1 is the first hidden layer, and layer capital L is the output layer. And we call the activations in every layer XL. So the activation at the output of a given layer or the input to the next layer, XL plus 1, are given by taking the activations before the current layer or the outputs of the last layer, XL. Then we apply this XL vector to the weight matrix WL in order to compute the weighted sums. And we add the bias vector BL. We push this whole thing through the nonlinear activation functions of the neurons, and that gives us the output of this layer or the input to the next layer. So trainable here are the weight matrix WL and the bias vector BL. So we will often need access to the argument of the nonlinear activation function. This is basically the internal activation of every neuron before we push it through the activation function. And because of this, we will give it a name and we will call this CIL for layer L and neuron number I. Now, what we want to do first is we want to compute the gradient of the loss or the derivative of the loss function with respect to the activations of the last layer. The activations of the last layer, those are just the outputs or the predictions of the neural network. So really what we want to do here is we want to compute the derivative of the cost function or loss function with respect to the outputs or predictions of the neural network. So we just take our loss function and we do this. So interestingly, we often have the following form of the loss function. We have something like 1 over n times the sum over all data points times a loss function contribution of every single data point. For example, for the mean square error, this is just the sum over the square differences of predictions minus label or label minus prediction. And then if we take the derivative here, this turns out to have a similar form. It's just 2 times the sum over the differences. So the loss function needs to be differentiable, but then we can in principle easily do this for every differentiable loss function. And all we need to do here is to do this once for every loss function that we consider and store this in our program or in our neural network package so that we can essentially just use it or apply it as a building block. But now we need to really go into backpropagation and ask the question, how do we get gradients? How do we get derivatives of the loss function with respect to internal activations within the neural network, and how do we get derivatives with respect to changes in the parameters? Because that is what we need in order to change the parameters so as to minimize the loss function. So an important intermediate quantity that we need is the so-called error vector. This is more or less something like a sensitivity. So the word error is, in my opinion, a little bit misleading. Think of it as a sensitivity of the output with respect to some intermediate activations. And it is defined as follows. It is the derivative of the loss function with respect to the internal activation of neuron number I in layer L. We stay at the last layer here for now, capital L, but this is true for every intermediate layer, little l as well. So what is this error vector? Well, it is defined as this derivative of the loss with respect to the internal activation, and that is equal to the activation, to the derivative of the loss function with respect to the output of that neuron, multiplied by the derivative of the output of that neuron with respect to the internal activation of that neuron. So this is just chain rule applied to this one neuron here. So what do we have here? We have as a first part the derivative of the loss function. And this we have already worked out on the last slide. The second part is the derivative of the activation function, the nonlinear activation function of this neuron. And again, this is something we only need to define once or code once for a given activation function that we want to use to build neural networks. And then we can reuse this every time we want to compute these errors. And it is shown below for a logistic activation function. So sigma prime in blue shows the derivative of the of the logistic activation function. So now the key step of backpropagation is how to backpropagate these errors. So we now are searching for an expression of the error at layer L, little l, for any arbitrary L. And that is again defined as the derivative of the loss function with respect to the activations, the internal activations of the neurons in that layer. So now, using the chain rule again, we can write this as a sum over the neurons in the next layer of the derivative of the loss function with respect to the internal activations of the neurons in the next layer, multiplied with the derivatives of the activations in the next layer with respect to the activations in this layer. So that is the key step here. We have related the activations of the next layer and this layer. And by doing several more steps of algebra, we can show that with this we can express the error vector in the current layer L as a function of the error vector in the next layer, L plus 1. And what we need additionally is the activation of the derivative of the activation function. We need the current activations, the internal activations of the neurons, ZIL. So we need to store the current state of the network, and we need the current set of parameters, in particular the weight matrix. And with this we can express the error vector in the last layer as a function of the error vector in the current layer, or the error vector of the current layer as a function of the error vector in the next layer. And because we go this way, we compute the current error vector as a function of the next one. We say we backpropagate the error. Yeah? We start with the expression of the error in the last layer shown on top of this slide, and we work ourselves back through the network and compute the error vector in each layer until we are at the beginning of the network. Yeah? So we evaluate the network in forward direction in order to predict an output, and then we evaluate it in backward direction in order to compute these error vectors. And now the last step of backpropagation is that we use these error vectors, or sensitivities as you might call them, in order to compute the gradients of the weights. So you take what you're really interested in is the derivative of the loss function with respect to a parameter of the neuron network, such as a bias at neuron I in layer L, or such as the weight matrix at layer L between neurons I and J. And then with the expressions from the last slide, and again using the chain rule of differentiation, you can show that these derivatives have simple expressions in terms of the error vector. So the derivative with respect, or the loss derivative with respect to the bias is simply the corresponding element of the error vector, and the derivative of the loss function with respect to the weight, so one element of the weight matrix, is simply the corresponding element of the weight of the error vector multiplied with the corresponding activation of the neuron in the last layer. So this is also why we need to store the activations of the neural network in order to compute these numbers. And then once we have this, we can update the weights. So now we can update the biases and the weights by changing them a little bit against the direction of the gradient. And here the step size or learning rate eta tells us how much we do that in every step. So this defines backpropagation. And we have earlier defined forward propagation. So how do we evaluate a network in forward direction to make a prediction? And so then an iteration of training a neural network is always this going back and forth between forward and backpropagation. So first of all, we have an activation at the input layer, the input activations. Then we evaluate the network feed forward. So for each layer, we compute the weighted sum and the nonlinear transformation, the nonlinear activation function, and get therefore the output activation of the neurons at that layer. Finally, we have reached the output layer. We compute the loss function. We compute the error at the output layer, which is the derivative of the loss function, or which uses the derivative of the loss function and the derivative of the activation function. And then we backpropagate the error using the algorithm shown on the previous slides. And finally, we calculate all the gradients of the loss function with respect to all the trainable parameters of the neural network. And we then change those weights by going a little step opposite of the gradient. And if we follow this procedure, we can completely automate it. And this is exactly what's happening in software such as TensorFlow, PyTorch, JAX, etc. So let us talk a little bit about software. I should add a new member to this slide, which is JAX. But for now, what we have here is Keras, Theano, TensorFlow, and PyTorch. So just to give you an idea of how these packages relate. So Keras is a high-level Python package. It's relatively easy to learn, but because it's high level, it has somewhat limited flexibility. It runs on CPUs or on GPUs, and you can install it either directly with pip or in principle you can also install it with Conda, but then you have to be a little bit careful that you have a compatible version of TensorFlow or Theano. Theano is a relatively old package. It was one of the first widely used packages to build neural networks or to do deep learning, but it is not really used much anymore. So basically TensorFlow and PyTorch have pretty much taken over that role. Keras was built to provide a high-level interface. Now the situation has somewhat changed because in TensorFlow 2, Keras has really become a member or a part of TensorFlow. So now Keras is a high-level package within TensorFlow. So using Keras or TensorFlow is quite natural to do that together. PyTorch is a little bit outside this Keras TensorFlow conglomerate. It is simplified low-level Python package for GPU accelerated tensor operation. It is a little bit harder to use than Keras, I think, but it gives you very direct and easy access to individual operations, elementary operations. And you can pretty much think of PyTorch as doing numerical calculations similar as in NumPy, but now you also have automatic differentiation and you can essentially build automatically computational graphs and use them for parameter learning. Okay, so finally, I want to